An electromagnetic pulse, also sometimes called a transient electromagnetic disturbance, is a short burst of electromagnetic energy. Such a pulse may occur in the form of a radiated electric or magnetic field or conducted electrical current depending on the source, and may be natural or man-made. The term electromagnetic pulse is commonly abbreviated to the acronym EMP. EMP interference is generally damaging to electronic equipment, and at higher energy levels a powerful EMP event such as a lightning strike can damage physical objects such as buildings and aircraft structures. The management of EMP effects is an important branch of electromagnetic compatibility engineering. The damaging effects of high-energy EMP have been used to create EMP weapons. These are typically divided into nuclear and non-nuclear devices. Such weapons, both real and fictional, are gaining awareness from the public by means of popular culture. General characteristics: an electromagnetic pulse is a short burst of electromagnetic energy. Its shortness means that it will always be spread over a range of frequencies. Pulses are typically characterized by the type of energy, the range or spectrum of frequencies present, pulse waveform, shape, duration and amplitude. The last two of these, the frequency spectrum and the pulse waveform, are interrelated via the Fourier transform and may be seen as two different ways of describing the same pulse. Types of energy. As with any electromagnetic signal, EMP energy may be transferred in any of four forms: electric field, magnetic field, electromagnetic radiation, electrical conduction. In general, only radiation acts over long distances, with the others acting only over short distances. There are a few exceptions, such as a solar magnetic flare. Frequency ranges. An EMP typically contains energy at many frequencies from DC to some upper limit depending on the source. The whole range of concern is sometimes referred to as DC to daylight, with optical and ionizing ranges usually being excluded. The highest frequencies are present in nuclear EMP bursts. These continue up into the optical and ionizing ranges. Some types of EMP event can leave a visible trail, such as lightning and sparks, but these are side effects of the current flow through the air and are not part of the EMP itself. Pulse waveforms. The waveform of a pulse describes how its instantaneous amplitude changes over time. Real pulses tend to be quite complicated, so simplified models are often used. Such a model is typically shown either as a diagram or as a mathematical equation. Most pulses have a very sharp leading edge, building up quickly to their maximum level. The classic model is a double exponential curve which climbs steeply, quickly reaches a peak and then decays more slowly. However, pulses from a controlled switching circuit often take the form of a rectangular or square pulse. In a pulse train, such as from a digital clock circuit, the waveform is repeated at regular intervals. EMP events usually induce a corresponding signal in the victim equipment, due to coupling between the source and victim. Coupling usually occurs most strongly over a relatively narrow frequency band, leading to a characteristic damped sine wave signal in the victim. Visually it is shown as a high-frequency sine wave growing and decaying within the longer-lived envelope of the double exponential curve. A damped sine wave typically has much lower energy and a narrower frequency spread than the original pulse, due to the transfer characteristic of the coupling mode. In practice, EMP test equipment often injects these damped sine waves directly rather than attempting to recreate the high-energy threat pulses. Effects: minor EMP events, and especially pulse trains, cause low levels of electrical noise or interference which can affect the operation of susceptible devices. For example, a common problem in the mid-20th century was interference emitted by the ignition systems of gasoline engines, which caused radio sets to crackle and TV sets to show stripes on the screen. Laws had to be introduced to make vehicle manufacturers fit interference suppressors. At a higher level, an EMP can induce a spark, for example when fueling a gasoline-engined vehicle. Such sparks have been known to cause fuel air explosions and precautions must be taken to prevent them. A large EMP can induce high currents and voltages in the victim, damaging electrical equipment or disrupting its function. A very large EMP event such as a lightning strike is also capable of damaging objects such as trees, buildings and aircraft directly either through heating effects or the disruptive effects of the very large magnetic field generated by the current. An indirect effect can be electrical fires caused by heating. These damaging effects have led to the introduction of EMP weapons. Most engineered structures and systems require some form of protection against lightning to be designed in. Types of EMP. An EMP arises where the source emits a short-duration pulse of energy. The energy is usually broadband by nature, although it often excites a relatively narrow-band damped sine wave response in the victim. Some types are generated as repetitive and regular pulse trains. Types of EMP divide broadly into natural, man-made and weapons effects. Types of natural EMP event include, lightning electromagnetic pulse. The discharge is typically an initial huge current flow, at least mega-amperes, followed by a train of pulses of decreasing energy. Electrostatic discharge, as a result of two charged objects coming into close proximity or even contact. Types of man-made EMP event include, switching action of electrical circuitry, whether isolated or repetitive. Electric motors can create a train of pulses as the internal electrical contacts rotate. Gasoline engine ignition systems can create a train of pulses as the spark plugs are energized. Continual switching actions of digital electronic circuitry. Power line surges. These can be up to several kilovolts, enough to damage electronic equipment that is insufficiently protected. Types of military EMP include, nuclear electromagnetic pulse, as a result of a nuclear explosion. A variant of this is the high-altitude nuclear EMP, which produces a pulse of a much larger amplitude and different characteristics due to interactions with the Earth's magnetic field. Non-nuclear electromagnetic pulse weapons. Lightning. Lightning is unusual in that it typically has a preliminary leader discharge of low energy building up to the main pulse, which in turn may be followed at intervals by several successively smaller bursts. Electrostatic discharge. ESD events are characterized by high voltages of many kilovolt but small currents and sometimes cause visible sparks. ESD is treated as a small, localized phenomenon, although technically a lightning flash is a very large ESD event. ESD can also be man-made, as in the shock received from a Van de Graaff generator. An ESD event can damage electronic circuitry by injecting a high-voltage pulse, besides giving people an unpleasant shock. Such an ESD event can also create sparks, which may in turn ignite fires or fuel vapor explosions. For this reason, before refueling an aircraft or exposing any fuel vapor to the air, the fuel nozzle is first connected to the aircraft to safely discharge any static. Switching pulses. The switching action of an electrical circuit creates a sharp change in the flow of electricity. This sharp change is a form of EMP. Simple electrical sources include inductive loads such as relays, solenoids, and the brush contacts in electric motors. Typically these send a pulse of voltage and/or current down any electrical connections present, as well as radiating a pulse of energy. The amplitude is usually small and the signal may be treated as noise, or interference. The switching off or opening of a circuit causes an abrupt change in the current flowing. This can in turn cause a large pulse in the electric field across the open contacts, causing arcing and damage. It is often necessary to incorporate design features to limit such effects. Electronic devices such as valves, transistors and diodes can also switch on and off very fast, causing similar issues. One-off pulses may be caused by solid-state switches and other devices used only occasionally. By contrast, the many millions of transistors in a modern computer may switch repeatedly at frequencies above 1 GHz, causing interference which appears to be continuous. Nuclear and high-altitude nuclear. NEMP is the abrupt pulse of electromagnetic radiation resulting from a nuclear explosion. The resulting rapidly changing electric fields and magnetic fields may couple with electrical electronic systems to produce damaging current and voltage surges. In military terminology, a nuclear warhead detonated hundreds of kilometers above the Earth's surface is known as a high-altitude electromagnetic pulse device. Typically the HEMT device produces the EMP as its primary damage mechanism. The nuclear device does this by producing gamma rays, which in turn are converted into EMP in the mid-stratosphere over a wide area within line of sight to the detonation. NEMP weapons are designed to maximize such effects, especially on electronic systems, and are capable of destroying susceptible electronic equipment over a wide area. The popular media often depict such EMP effects incorrectly, causing misunderstandings among the public and even professionals, and official efforts have been made in the USA to set the records straight. Non-nuclear electromagnetic pulse. Non-nuclear electromagnetic pulse is a weapon-generated electromagnetic pulse without use of nuclear technology. Devices that can achieve this objective include a large low-inductance capacitor bank discharged into a single-loop antenna, a microwave generator and an explosively pumped flux compression generator. To achieve the frequency characteristics of the pulse needed for optimal coupling into the target, wave-shaping circuits and/or microwave generators are added between the pulse source and the antenna. Vircators are vacuum tubes that are particularly suitable for microwave conversion of high-energy pulses. NNEMP generators can be carried as a payload of bombs, cruise missiles and drones, with diminished mechanical, thermal and ionizing radiation effects, but without the political consequences of deploying nuclear weapons. The range of NNEMP weapons is much less than nuclear EMP. Nearly all NNEMP devices used as weapons require chemical explosives as their initial energy source, producing only 10⁶ the energy of nuclear explosives of similar weight. The electromagnetic pulse from NNEMP weapons must come from within the weapon, while nuclear weapons generate EMP as a secondary effect. These facts limit the range of NNEMP weapons, but allow finer target discrimination. The effect of small E-bombs has proven to be sufficient for certain terrorist or military operations. Examples of such operations include the destruction of electronic control systems critical to the operation of many ground vehicles and aircraft. The concept of the explosively pumped flux compression generator for generating a non-nuclear electromagnetic pulse was conceived as early as 1951 by Andrei Sakharov in the Soviet Union, but nations kept work on non-nuclear EMP classified until similar ideas emerge in other nations. Electromagnetic forming. The large forces generated by electromagnetic pulses can be used to shape or form objects as part of their manufacturing process. Control. Like any electromagnetic interference, the threat from EMP needs to be controlled. This is true whether the threat is natural or man-made. Therefore, most control measures focus on the susceptibility of equipment to EMP effects, and hardening or protecting it from harm. Man-made sources, other than weapons, are also subject to control measures in order to limit the amount of pulse energy emitted. The discipline of ensuring correct equipment operation in the presence of EMP and other RF threats is known as electromagnetic compatibility. Test simulation. To test the effects of EMP on engineered systems and equipment, an EMP simulator may be used. A small-scale ESD simulator may be handheld. At the other end of the scale, large outdoor test facilities incorporating high-energy EMP simulators have been built in the United States, the Soviet Union, the United Kingdom, France, Germany, the Netherlands, Switzerland and Italy. The largest facilities are able to test whole vehicles including ships and aircraft for their susceptibility to EMP. Information about the EMP simulators used by the United States during the latter part of the Cold War, along with more general information about electromagnetic pulse, is now in papers under the care of the SUMMA Foundation, which is hosted at the University of New Mexico. The SUMMA Foundation website documents the huge wooden Atlas I simulator at Sandia National Labs, New Mexico, which was the world's largest EMP simulator, and nearly all of these large EMP simulators used a specialized version of a Marx generator. The SUMMA Foundation offers a short documentary on its website called Trestle, Landmark of the Cold War. The U.S. Navy also has a facility called the Electromagnetic Pulse Radiation Environmental Simulator for ships IEMP in fiction and popular culture. Lightning has long been used as a dramatic device in popular fiction. In some tellings of the Frankenstein story, The monster is animated by a lightning strike. References to EMP weapons in popular fiction go back at least to 1965, however EMP did not gain a significant presence until the mid-1980s. The popular media often depict EMP effects incorrectly, causing misunderstandings among the public and even professionals, and official efforts have been made in the USA to set the records straight. See also. References. Sources: Gladstone, Samuel. Dolan, Philip J. The Effects of Nuclear Weapons. United States Department of Defense and the Energy Research and Development Administration. A.